Do you try to drink?
No, it just happens. Sometimes I'm doing on the Super Saiyan.
No, you don't try everything. You don't try anything.
No, I tried something
Food.
once.
Food.
Food? Yeah. Food?
Yeah.
Meals?
We did that, right?
Yeah.
There was a response.
Did you ride the Humber last time?
Never. Ever.
Yeah.
Never will I.
Okay, you ride the Humber last time?
Everything for one first, man. Everything for one first.
Okay, so this is where we stopped last time. Okay, then I expect you did the exercise. So that functions as your preparation, right, for exam.
You know, talking in for the exercise, if we do it and we're not sure the answer, do you have the answer or just
check with your group member and argue about it.
Yeah, that's.
So that's the way to study, you know.
No, that is the way to study.
Check with your group member. If you don't get the same answer, then you
Yeah.
debate.
But
See
what if we
who's
get-
right.
What if we get all the same answer, but it's all?
But
it's
before
wrong?
you get into fist fight, come talk with me, right?
Okay.
So group member, or you can check with another group. If your answer is so different than two groups, you know, majority of the people against you, then you lose, right? So then you learn from others, and then the next time they learn from you too. So don't jump to just get the answer, you know. Try to understand where you made a mistake. Okay. Okay. Continue with complexation, reaction, and titration equilibria. So that is a complexing agent. An example is ammonia. Call that a ligand. And it's called monodentate ligand. Mono meaning one. So the one refers to the binding site. So for that ammonia, you can see there are two electrons available for forming one bond. So there's one site, so it's mono. Now polydentate, that means more than one. So as an example, ethylene or ethyl-diamine group has two sites available. So this is a bi, you know, the bidentate ligand. Okay.
I'm sorry. Could you say that one time?
What else do you need to know?
With the words, with the binding sites, you said ethyl-diamine.
It's all up here.
Because the lone pair.
So it's poly meaning more than one. Specifically for two, then it's bi. So you have two sites available for binding.
Okay. Yeah. Okay. All right.
Okay. So binding to who? Well, to the metal. So the metal is an ion, a cation. For example, copper is a 2+. But these ligands are neutral, so the product is going to carry the charge of the metal. Okay? So notice this complex, the net charge is 2+. Okay? Then here, complex with ammonia, then also neutral, then it's 2+. Look at the ethyl-diamine molecule. It bends so that the orientation of the two bonding sites will form a bond like that, so it's bent to form a structure. Now here is a mono, right? Mono is at one side, so it's straightforward, just one bond. And here you have two bonds to one ligand. Okay, the shorthand to write this formula, use En to represent the ethyl diamine. So two molecules of En to one ion to form this complex. So this is the formula. Okay, the bond here is sharing of electron, right? So sharing is covalence bond. The nature of covalence bond is sharing. But in inorganic chemistry or coordination chemistry, the way this bond is formed is called coordination bond, which has no difference to covalence bond, okay? But initially, the way it is formed is coordination. So the electrons will come from the ligand, okay, and fallen into the d orbital and share to form the covalence bond. Yes?
So in the NH2 right there, what is the charge for the NH2?
No, you took organic chemistry, right?
Yeah.
So here will be hydrogen, CH.
No, yeah.
Two. This is neutral, the whole deal is neutral.
Yeah, in the compound with the ligand.
The 2 plus, the whole complex.
Yeah, but what about use the nitrogen? Because I was told in organic that nitrogen can have only 3 bonds, and there it has 4 bonds. Is it gonna have a charge?
No, this is the sharing of the 2 electrons. So this is a bond. This is a physical bond. Right? So there's a coordination bond come from the 2 dots, the 2 electrons. Okay? So notice you have 2 electrons here, 2 electrons here. Originally 3 bonds, but the 2 electrons form a bond with the central metal, and therefore
So
4 bonds.
Is there a positive charge in the N, in the nitrogen?
No. Sharing an electron, no change. You know, the 2 electrons are fallen into the d orbital. Yes?
What does it say in the parentheses, Cu something to DH?
This parenthesis?
Yeah, I just don't know what that.
Okay, parenthesis just to represent this whole
It's En.
Yeah.
En. Yeah, the En only. Parenthesis meaning is just this deal.
So what's
En,
is En?
En is the ethyl diamine.
Yeah, right.
That's
E,
okay, thank you.
En, not Ed. You know, En looks better than Ed. Okay, so otherwise, you know, you write such a long formula for analytical chemists, they think is inefficient. Did I answer your question? You still kind of puzzled about it?
I still don't understand the.
Remember, sharing electron nothing has changed on the charge. The 2 electron fall into the d orbital are available in the central metal. So there's no charge difference. Okay, the 2
So
electrons
it's
now
not really a
form
bond then?
It's an interaction. Interaction, right?
It's not technically a bond then.
When you take inorganic chemistry,
He said.
so that will be better understood
So that
Okay.
holds true for when you're.
for preliminary. D, 1, 2, 3, 4, 5, right? So you have ammonia here,
That's it. It's just breaking the rule.
2 electron. So the 2 electron will just fall into it, then you form a physical bond. Then originally, this central metal may itself have electrons available already, okay? So things like that. So this is a falling and fulfill it. In this case, it will accept just 1 ammonia. But in reality, for example, for copper, it's going to have 4 empty d orbitals available, and therefore ammonia 1, ammonia 2, ammonium 3, ammonium 4. So it's totally complete, okay, that kind of thing. But take chemistry 1, 2, 3. Is dedicated to coordination chemistry. Okay, so same here, there's no charge, okay, just 4 bonds. So these become coordination bond, which is the same as covalent sharing bonds, okay. So now talking about stability, you can use your inorganic chemistry or organic chemistry to explain, right? Looking at the structure, then you can explain which complex is more stable. But in analytical chemistry here, we leave the explanation to those folks. But we can perform calculation to prove which one of the two is more stable. Now, for those of you who have taken organic chem, I believe so, is prerequisite, right? 128. So which one would you predict to be more stable? How many people say that this one is more stable? Raise your hand. So the rest of you would think this is more stable, right? So how many say this one is more stable? Four people, and Anton, not sure. You should know, right? Through explanation, this is more stable. See, this guy, single bond, is going to flip around. And here, 5-membered ring, right? You learn in organic chemistry, 5-member ring would make a stable structure. So this, through explanation, it is more stable, okay? So through calculation to prove, then you simply look up the table for the K of formation.